Hello everyone, my name is Caroline and today I'm going to talk to you about RLCheck. So you may know that programs have bugs, and if they're in the wrong software component, these bugs can be really expensive and even cause security vulnerabilities. On top of that, they're sometimes hard to find. So one of the best ways we have of communicating bugs to each other is actually when we can find inputs which reveal bugs in programs. Inputs that, when you run them through your program, the bug is clearly demonstrated. So in recent years, we've seen the emergence of fuzzing tools, which work to automatically create inputs, which reveal such bugs in programs. And those fuzzing tools have been adopted quite widely across industry and open source to find bugs and improve the quality of software. Now today, I'm going to focus on a particular type of fuzzing called generator-based fuzzing. I'm going to talk to you about the fundamental trade-off with generator-based fuzzing and how RLCheck helps address it. So you may have heard the term fuzzing back in the 90s when Martin Miller and others discovered that if you just take random sequences of characters and send them to popular Unix utilities, eventually some random sequence of characters may actually cause that popular Unix utility to crash. Now, in the 30 years since then, fuzzing tools have become substantially more sophisticated as programs are hopefully robust to just pure sequences of characters. So what happens now if you want to fuzz, say, the Google Closure compiler, which expects JavaScript inputs? If you just send it pure random characters as inputs, pretty quickly you'll figure out that it does not look like JavaScript. You'll immediately exit. You won't find any interesting bugs in the program. So the idea of generator-based fuzzing is quite simple. Basically, instead of having a random source that's generating your random inputs, you have a specific input generator, which is a function that's non-deterministic, and each time you call it returns kind of a random input, but that's in a given input space, here say JavaScript programs, so that your test program will actually do stuff, and hopefully you'll actually find interesting bugs in your program. Now I'm going to get into a little more detail on generator-based fuzzing by looking at a much simpler example. In particular, we're going to consider a case where our input space are binary trees. The nice thing about that is I can show you a binary tree generator on a single slide. Here's a program that generates random binary trees. It does this by first selecting a random value for the node of the tree. Say that's 2. Then it might choose whether or not to generate a left child randomly. If it does, it'll recursively call genBinaryTree to generate the whole tree rooted at that left child, which starts with choosing a random value for the node, and so on and so forth. To discuss the fundamental trade-off, we're also going to actually have to look at a program that accepts binary trees. Here is one such program. This program tests whether the binary search tree insertion function actually preserves the binary search tree property. And the nice thing here is that we can use this handy assume statement, which returns early if the tree is not a binary search tree, to use our regular binary tree generator and just do rejection sampling to try and generate hundreds and thousands of inputs to this program, just rejecting any inputs at this assume statement if they're not binary search trees. Now, as you might imagine, there might be a problem here if we have too many rejections. And that brings us to the big trade-off we have in generator-based fuzzing. How many rejections do you think we have in generating binary search trees here? Well, if we consider the case we were in again, where we've chosen 2 for the value of the root node, to preserve the binary search tree property, this needs to hold. So the only valid choices for the left child are 0 and 1. So that's already what, like less than 11% chance of generating a binary search tree here. We're not going to generate many binary search trees of size greater than, say, 2 with this binary tree function generator. So one thing we could do is, manually tune this generator, make sure it only generates binary search trees, but that's work that's only going to work for this particular driver that accepts binary search trees. Or otherwise, we'll just have to suffer a really bad fuzz test that only generates binary trees of very small size and very rarely. And because the time spent tuning generator gets a lot larger as we're looking at more complex validity functions, it's why it's a big trade-off in the time you spend tuning it versus the effectiveness of your fuzz test. So how may RLCheck help? The high-level idea is that instead of your generator just generating random inputs, it's going to be guided by a guidance that's educated by whether the last choices the generator made resulted in a valid and unique input. Fundamentally right, the generator is capable of generating a binary search tree. And what we want to do with RLCheck is make sure the generator always chooses, 0 and 1 in this case, without having to modify the code. So effectively, what we just need to do here in RLCheck is guide these random choices so that they always return values that maximize the chance of generating a valid input. Now, of course, the best choice depends on the context of that choice, right? 0 and 1 are good choices if you're the left child of the two, but not if you're the right child of the two, or if you're the left child of a 7, which is the right child of a 2. So really, RLCheck is also going to have to solve a problem where it's making the best choice given some context. I don't have time to go into what exactly context is here, but you can basically think of it as an abstraction of the prior choices made by the generator. So what we need are guides that make the best choices given the context, which sounded a lot like a problem maybe reinforcement learning could solve. So what we did in RLCheck is have a table-based Q-learning agent at each choice point in the generator. We compared RLCheck to both just regular generator-based fuzzing, as well as our prior work using evolutionary algorithms to guide fuzzing, that's ZEST in the orange. And what we find is that RLCheck in the green was able to generate orders of magnitude more unique valid inputs in the same time frame. And this held on most of our benchmarks, except C Rhino, which you can see that QuickCheck was already pretty well suited for that benchmark. All right, generator-based fuzzing can be really effective if you tune your generators well, but that can be hard to do. What RLCheck does is it uses reinforcement learning to bias the generator towards generating more unique valid inputs. You'll find more details in the paper, and you can find the code here as well. And I'm happy to take any questions. Thanks.